Hi everybody, I'm Razvi. Welcome back to another video from the PWN101 series. This video is the second installment of the Advanced Format String Vulnerabilities video, whose first part has been already published. In case you didn't already, I recommend you watching it. In the first part of this video, we have seen what the internal buffer of the vfprintf function is, how we can find it in memory, and most importantly, how we can abuse it by exploiting the printf function in order to modify the positional arguments on the fly. In short, bending printf to our will and weaponizing it into a write what where primitive. In this second part, we will see the other solutions from this challenge. Let me remind you, we are solving the sniper challenge from TAMUctf 2025. As always, everything you see on the screen will be correspondingly linked in the description below. So let us jump straight in. Just a very small recap. Let us remember that in this challenge, our input, the input the user provides to the binary, lives at the 6th position from the printf perspective. Also, our flag is stored in memory at this address, which was a tricky one, because the A character, 10 in hex, corresponds to the new line character. Given that the input is read with the fgets function, we cannot just write A in hex, because fgets will understand that we pressed enter and it will finish. And also, very important, fgets in this challenge reads up to 30 in hexadecimal or 48 in decimal bytes. And that's basically it. If you want to know more about the binary itself and its disassembly, please refer to the first video, to part 1. So now let us take a look at the official solution as published by the TAMU team once the CTF was done. You can find it in their repository on GitHub. They are using the n format specifier to write the 0A value at a certain position of memory that is then later parsed with the s format specifier as a string. And given how this whole payload looks like, you can already imagine that we are somehow referencing with the n format specifier this address we have right here, and remember the n format specifier expects a pointer, an address that will be later dereferenced. And the address written at this position that will be dereferenced happens to be this memory position we have right here. As you can see, we have all null bytes in this specific memory cell because we are writing them by hand. The null byte is not a bad char for the fgets function. And then by writing at a very particular memory position the 0A values, we are able to successfully read the flag by referencing that memory position with the s format specifier that once again it dereferences the value, in this case the memory address, and parses it as a string. Since that memory address will be our flag, ideally we will be printing our flag. Alright, so let us go step by step with this payload. The nodes we have here as a comment are actually helpful for us in order to understand what is going on and what each format specifier is actually performing. We have the printf positions, and remember that our input starts at the 6th position from the printf perspective, and that means that each 8 bytes we are writing one position. That's why we have the 6th position, then we have the 7th position, and so forth. Then we have the memory cells written, which is a little hint for us in order to know how many memory cells we have written so far. Every 8 bytes we advance one printf position and we increase the memory cells written. This is only helpful because remember we can write as much as 6 memory cells, so it is just like a little help for us. And then, last but not least, in fact that's the most important thing, we have the printf internal pointer. And here is where we have to make sure we understand how printf internally works. Remember that with each format specifier, we advance the printf internal pointer by one argument or one memory cell. Every format specifier, which starts with a %, indicates that we want to print the next printf parameter. Just as a quick reminder, if I have a printf call of these sorts, the first format specifier will reference the first argument given to the printf function, excluding of course the very format string itself. That means that this first format specifier will attempt to print as a string the A string I have right here. Now, as you can see here, there are no more arguments to this printf function. However, there are more format specifiers. So the printf function will do as it was instructed. It will keep dereferencing and trying to access further parameters, even if there is none. And that's how the internal printf pointer works. So that's what we are doing here with the payload. So this number we have right here represents which memory cell from the printf perspective is its internal pointer actually pointing to. This means that when the printf function executes this format specifier, its internal pointer will be pointing to the 6th memory position, which also corresponds to our input. It means that this format specifier will be pointing here. That being said, when the printf function executes the following format specifier, which is this %c we have here, it increases the internal pointer 1 memory cell, pointing to the 7th position. That means that this %c will be pointing here. Likewise, when it executes the next format specifier, that means that this %c will be dereferencing this memory cell, and so forth. And now, before talking about the half right we have here, let us understand what these numbers are. How many bytes are we printing here? The C format specifier prints a single byte, that is a char, and here we are printing 8 of them. So when we reach the N format specifier, which will write the number of bytes printed so far, it will attempt to write 8, given these chars printed here, plus we are printing here a single char but padded with 2562 bytes, which give us a total amount of 2570 printed bytes, which in hex corresponds to A0A, which is indeed the memory address where our flag is living. Of course, we must somehow pad additional zeros, but we will deal with this a bit later. Alright, now we know how many bytes we have printed so far. Let us think a bit for a moment, where will this N format specifier actually write this value? First of all, notice we have the half sublength specifier here, which means that we will be writing only 2 bytes. Remember that by default, the N format specifier writes 4 bytes. And the printf internal pointer will reference the 10th position. Now, what is this 10th position? Well, remember that here we have tracked the memory positions from the printf perspective, so the 10th position will actually be the one we have here. This means that whenever this N format specifier will be executed, it will write only 2 bytes, and printf's internal pointer will be pointing here. Now, what is this value? Well, remember that the binary, when executed, it's leaking the address of the buffer. That is the address where this very payload will begin. The beginning memory address of the user's input. And what is this plus 42 magic number we have right here? Well, bear in mind that 40 is actually 5 memory cells, because if we divide 40 by 8, we get 5 memory cells and 2 additional bytes. What's the reason behind this? Well, because leak will be pointing to the very beginning of the buffer, which is the 6th position. Then we sum 5 memory position. This will make us point right here at the 11th position, and 2 additional bytes, because remember that we don't want to write at the very beginning of the number. We want to write 2 bytes past it. Well, now let us suppose we want to write a number like this. This is the 11th position. This is plus 1. And this is plus 2. That's the very reason why we have here leak plus 40 plus 2 plus 42. In other words, think that this P640 will fulfill with null bytes, and then we want to write with the N format specifier starting at the very beginning of this memory plus 2 bytes. And in case you are wondering, these A's you see here are just for padding purposes. So everything gets aligned to their corresponding position. So to sum things up, this solution is very similar to the one we saw in the first part of this advanced format string series, only it doesn't use any positional argument. While this solution may be a bit more conceptually difficult, once your brain clicks, it will become pretty simple. When the N format specifier will start writing, it will point to this value and will be dereferenced here. That means that it will write something like A A0A. And this A0A is actually the address of our flag. Then, given that our next format specifier is the S format specifier that dereferences a particular address and prints it or attempts to print it as a string, this %sign here will push the internal printf pointer one position farther, making it point to the 11th position, which is what we have here. But since we modified it previously, it won't point to null bytes, it will rather point to the value you see here on the screen, thus printing the flag. And now let us actually test it to see if it works. Just like before, we will launch our exploit with the dbg parameter, so we get spawned a GDB shell. And now we will select solution number 1. We just have to continue, as it will all happen in one single execution. This time there won't be an internal buffer that stores the original value of the arguments, so ideally, we will be able to print the flag as we modify where the S format specifier points to. And as you can see here, this is indeed correct. Remember, this is the fake flag I was using for the challenge, and we can actually print the stack in order to see our own payload. Here we have it. You will notice all the C format specifiers we used in order to pad the output and get N to write the value we desire, which happens to be this one right here. As I have already mentioned, this is leak plus 40, this is leak plus 41, and this is leak plus 42. Since HN writes 2 bytes and the value to write is A0A, we are effectively writing this value into the position we actually want. So this was an alternative solution for the challenge. In fact, it is the official solution, sort of saying, since it is the solution provided by the challenge authors, and it basically abuses the printf function without using any positional argument, so the internal vfprintf buffer comes into play. Now let us move on to the next solution, which is the one that overwrites the printf return address, forcing it to execute once again. Since this time we are indeed using positional arguments, the internal buffer will take place. But the trick here is that printf executes itself once again without modifying the payload originally provided during the first call, so it will get to print the modified version of the arguments. It will invoke the internal vfprintf buffer, saving the original values before I get to modify them, but I don't really care, because once they are modified, I will call printf once again with the modified version. So basically, before moving on and trying to understand every single detail about this payload, we have to bear in mind that we are fully weaponizing a write what where primitive given this format string vulnerability. And that is because the program, the originally vulnerable binary, is leaking us the buffer where the user input resides in memory. And given how this stack works, which we have seen in so many previous videos, we know that when the time comes for the printf function to return, once it finishes, the return address will be also placed on the stack in a previous stack frame. Since again we have a write what where primitive, ideally we should be able to overwrite the return address with arbitrary values. In this case, we will make printf execute again. And to better understand how we are about to do it, let us debug the execution. So we can use the start command, and we can see the execution is stopped right at main +4. Since we know that we are interested in the vuln function, we can write this as vuln, and we can place a breakpoint right when the vulnerable printf is about to be called, the one that will execute parse our malicious format string. And now we continue execution. The program is waiting for our input, and this is the address of our buffer on the stack. In this execution, I'm using this idiotic input. The execution is now stopped right when printf is about to be called, and let us this as printf as well. Since we are interested in knowing where the address of the printf function when it returns is on the stack, we can place a breakpoint right here at printf read instruction, so we can see, or we can inspect rather, where the RSP pointer will be pointing to. If you want to know more about this basic stack mechanism, I recommend you taking a look at the return-oriented programming video you can also find on this channel. So let us place a breakpoint here and we continue execution. So now the execution is stopped right when printf is about to return. We can use the disas command to see the whole code for the printf function. We can see here the RIP is pointing to this address. It is about to execute the read instruction. It is in situations like this when PWN101 comes in very handy with its contextual view, as everything we need in this moment we can see it in this very screen. For example, we can see that RSP here points to this address whose content is this another address that corresponds to vuln plus 103. That's where the execution is about to return when the read instruction gets executed. We can always use the stack command in order to see more. And in this case, we can already notice that the RSP register is pointing to this address, D8, and the user buffer, which is E0, is one memory position higher. This means, from our exploitation perspective, that when the printf function finishes, the return address that the read instruction will actually read lives at one position lower than our buffer. And that is leak -8, which is what you see here. Okay, so we know that the legit printf execution will attempt to return to this address, which is vuln plus 103. So let us take a look at the vuln function. It will attempt to return here, vuln plus 103. Since we want to call printf once again with the very same arguments, we can overwrite the return address to return instead of here. We can make it return just right here, which is basically the setup of the parameters that printf will actually read. And the good thing about this is that we only need to overwrite the least significant byte of this address. And we have to somehow write the D1 value right at the buffer -8 address, right within it. That means that we will be overwriting this E2 you see here with the actual D1. And what is this D1 value in hex? Well, let us take out. D1 corresponds to, in decimal, 209 bytes, which, if you notice, is the value we have here. We are printing a single char with 209 padding, and then we are using the half n format specifier to write where the 11th position from the printf's perspective points to. The 11th position is what we have just right here, at position 11, of course. Leak -8. In this case, we don't need any extra arithmetics regarding the addresses, because remember that half n format specifier writes a single byte. And now that we managed to override the return address of the printf function, what we need is to write somewhere in memory the address of the flag. In the previous solution, we were writing this full null bytes memory position by hand, only that this time we do not have enough room in our payload to write it by hand. But what we can do is take a look at how the stack is formed, and maybe we can find a position that actually contains full null bytes and we can overwrite it. Using the stack command in PWN101 and any given number, we get to see farther up the stack. And remember that this is the address the program leaks. How can you actually find which memory address on the stack is fulfilled with only null bytes? Well, you can basically debug repeated executions one after another until you find any particular offset that is fulfilled only with null bytes with zeros across executions. And in this case, we have this one right here. So now we only need to count the distance, the offset, from our buffer to this memory position. We can count it by hand, 1, 2, 3, 4, or we can use the dist command from PWN101, which stands for distance, of course. We said we wanted this address and this one right here, and we can see that the distance is 70 in hex bytes. In hex, what 70 corresponds to, and it corresponds to 112 bytes in decimal. And in fact, this is the number you see here, leak plus 112. You may wonder why there is a +2, and that is for the very same reasons as before. Alright, so at the position number 10, from our printf perspective, I am writing the memory address where I will be placing the address of the flag, which initially contains all null bytes. Now, of course, I need to keep printing another character with the enough padding so the total amount of bytes printed so far is the exact number that I need, that is 0A0A in hex. And luckily for us, this is a very easy operation. We have printed so far 209 bytes with the initial padding, and now we have to subtract from it the destination address we actually want, that is the address of the flag, which in decimal is 2570, and we get 2361, which is exactly the number you see here, 2361. Given these two numbers, the total amount of bytes printed so far will be actually A0A, which is the address of the flag. Now, we are using the half n format specifier, which will attempt to write 2 bytes, which is exactly what we want, and it will dereference the address contained in the 10th position from our printf perspective. So this n format specifier we have right here will attempt to dereference this address we placed here. And now the only thing remaining for us is dereferencing somehow this newly write address of the flag as a string, which is basically what we are doing here. You will notice we are dereferencing the 20th position from our printf perspective, and that is because the newly written address of the flag will be living at the 20th position from the printf perspective. This is also a very easy operation since we have 70 bytes in hex as a difference from our input. We can do the maths like this. We have 70 bytes of distance, which is 112 in decimal, and we divide it by 8 in order to see how many memory positions we have from our buffer, and it is 14. But remember that our buffer starts at the 6th position from the printf perspective. In total, there are 20 positions, which is exactly why you see here the 20. And it will hopefully print our flag. So now let us test it. I could launch the exploit in debug mode, but I think we debugged enough already, so this is solution number 2. Let us see whether it works. We see we have reached some infinite loop. However, we don't actually care given that we are indeed successfully printing the flag. Remember that we are actually trying to hack things, so in this case we don't care that much about a clean execution, a clean exit. If you want to actually debug this payload and see how the stack gets overwritten in real time, I encourage you to do so. Playing around and tinkering, fiddling with the exploits and the bytes itself, the memory, it's how you can better learn how stuff works. And now, last but not least, let us take a look at the final and fourth solution we have for this challenge. This solution is somewhat a bit more rudimentary, I would say, and also more inefficient. As you may already anticipate, in this case we are padding quite a lot of bytes, and in this solution we are printing over the network the whole number of bytes we actually need. As you can see here, the total amount of bytes we have to send over the network is actually 868 megabytes. You can see here it ends in 20. However, we are sending here some number that ends in 8. And why is that? Because the remaining bytes that we need will be actually printed with each of these single character prints. We are printing here a total amount of 12 characters, which summed, added to this value, we get the exact number we need to write. Now this solution is a bit tricky because it relies on a given pointer that is on the stack, which we will see in just a bit. So when we get to write with this long n format specifier, notice how this time we are not writing 1, 2 or 4 bytes. We are writing a full 64-bit address. We are writing here 8 bytes. It will dereference the address that will be contained in the 14th position from the printf perspective. And luckily, at this 14th position, we will have a pointer to the 18th position. That is, when this ln format specifier will attempt to write, it will dereference whatever is contained in the 14th position from the printf perspective, which will happen to be a pointer to the 18th position. We will write there a full 8 bytes memory positions, which would be equivalent to something like this. And then using the S format specifier that you see here, we will dereference the 18th position from the printf perspective, which will happen to contain this memory address, and we will print it as a string, ideally printing our flag. Before executing the solution, let us debug the program so we get to see how stack is formed right when printf is called. Just like before, I will be placing a breakpoint right when our vulnerable printf gets called. I will continue the execution. It waits for my input, let's say this string right here, which is easily identifiable. Execution is stopped right when the program is about to call printf. Let us this as printf once again, and we will break right here before returning. Let us continue, and now we are about to return to exit from printf. Let us inspect the stack right now, and we can see that here we have the buffer. Bear in mind, this is the 6th position from the printf perspective, and you will soon notice that here, some directions higher, we have a memory cell that contains an address which is also from the stack. It is the RBP register that points to the old RBP, which is this address right here. Now we can count the memory positions, and given that this is number 6 where the buffer is, this is the 14th position, it points to the 18th position. So using this approach, what we are doing is with the n format specifier, dereference whatever is contained at the 14th position, which happens to be the 18th position, this one right here. So we will overwrite all this address with 8 bytes that will correspond to 0A0A and so forth. And then for the last part, by using the S format specifier, we will be dereferencing that very same position. So now let us test it. We will invoke the 4th solution this time. And here I have an error which says printf is not defined because printf is not a Python function. So we will just fix that. And once again, I want the 4th solution. And as you can see here, we are printing all these padding bytes, and once it's done, you can see that we have the flag right here. In fact, there is a simple test we can do, which is redirecting the output any given file, let's say output.txt, but before, let me comment the debug log level. Let us execute it once again. It is now waiting for the solution, number 4, and now let us wait for it to finish. And now the resulting file, as you can see here, the output.txt, has a very similar size to what we have anticipated. In fact, if I were to execute the list command without the human readable flag or parameter, you see here the actual bytes this file takes, and the number is very familiar. Not exactly the number, the address of our flag, because there is some input from my Python script and also from the very execution of the program, but you can see that every single byte is actually printed to the file. In this video, we have seen 3 alternative solutions for the sniper challenge from TAMUctf 2025. This challenge involves exploiting a format string vulnerability. In this video, we have seen how we can exploit it without using any positional argument, how we can do it by overwriting the printf return address, and finally how we can do it by sending over the wire all the needed padding bytes, the amount of bytes we need in order to write somewhere the address of the flag and finally print it as a string. I hope you liked the video and found it useful. If there is anything you want to say, leave a comment below. And remember, exploit code, not people. See you in the next one. Until then, GG.